Good morning, folks. We're going to talk about volcanoes today. And here we're looking at Iceland, the most recent eruption that's been going on. They've had a series of swarms of earthquakes going off around this volcano, and as we can currently see, it is extremely active. Many people are gathering to take videos and photos of the lava flows and of the eruption, which to me seems, okay. But being Hawaiian myself, I find it foolish. I'm not going to want to sit around and, let's take a look at this. I mean, look at that just coming up. Speaking of Hawaii, no one seems to be giving much concern about Hawaii. Now, we're over here at earthquakes at volcanosdiscovery.com, and as we can see up here, this is Iceland. We can see all the swarm of earthquakes and stuff that was going on and the volcano erupting. But if you look along the ring of fire, all of these volcanoes, and yet all of these earthquakes are going off. Well, with all of these earthquakes, there's a lot of movement, and it's going to put pressure. It's going to put pressure right here, and look at this. Kilauea's volcano is going off, and yet nobody's really mentioning that. Oh, because they're used to it. Well, yes and no. One of the things that you have to look at is right here on the Big Island. This is one of the most active, it's the largest active shale volcanoes in the world. Now, it's not the largest in the world, it's the largest active volcano in the world. But it's not technically going off at this moment. There's a lot of unrest, and there's a lot of plumes that are coming off, and it is giving warning signs, but nobody's mentioning Hawaii. You see all the swarms that are going off? There's been over 69 in this area in the last 7 days. That's what all of these are, different colors, different days. So there is activity going on over here. Now, when it comes to volcanoes, I want to make a little tutorial here so we can kind of understand some volcanoes. This here is a typical volcano that we notice. You know, you got the sides coming up, and then it collapses down inside, and then you've got your ash tuff on top, right? And then basically your lava plumes, here kind of comes up to the surface. So we know about this. But what about these? You still see the lip that comes up and pops down, and then it kind of comes up and forms what could be almost like a mountain range. So you can still see the dip down, then you can see your sediments, okay? So this is another one that, we're very familiar with seeing, but not so much of an actual shale volcano like this. Okay, this right here would be what would be typical of a shale volcano. You got your collapse, where it collapsed down inside, right? Now this is an obvious cutoff, okay? Where it collapsed down and it plugged the hole, okay? Now, of course, with a bunch of rain and, let's say, mud floods, let's say a sleeping super volcano like Yellowstone, or a little something that people don't know about called Wawa Springs Caldera, where it's been sleeping for a long time, and we know that Yellowstone's been sleeping for a long time as well. And then you've got other things pushing it. You got, if you want to call it a mud flood, major flooding, and comes up. Well, what happens is this continues to push up, and then you have these little mountain ranges that get formed. And you would not be none the wiser. You could be up here, climbing this peak, would be way up here, and yet underneath your feet, right here would be magma flow, and you have no idea that it's even there. And let me give you a little example. Again, Wawa Springs Caldera. It is a super volcano eruption remnant discovered in 2013 in Utah. It emitted 5,500 to 5,900 kilometers cubed of tephra. Now, where is this thing? Now, this is about 30.06 million years ago, right? So it would be roughly asleep, if you will. Well, welcome to Wawa Springs Caldera. Look at the size. This is all scorched earth. All of this. Do you see the size of this thing? Look at the size of this. This is something that people need to take note of as well. And last year, there was a bunch of fires. Guess where? All around the edges of Wawa Springs Caldera. Fires all around this thing. Isn't that interesting? Why would there all of a sudden be fires around it? But when it comes to volcanoes and all these earthquakes and things going off, people have to understand why. Why are we getting all these earthquakes? Why are we getting all these volcanoes going off? Why are we getting all kinds of tectonic plate movement? Well, let me show you. It has to do with our sun. See, our sun is actually picking up in its solar cycle. We're supposed to be at a solar cycle minimum. And I'll show you that here in a moment. That actually relates to coronal mass ejections and flares. This right here we're looking at is a huge ribbon of plasma being released from the sun. It is a coronal mass ejection, positively charged plasma lifting off of the sun and hurling towards Earth and impacting Earth. Okay? Now, Experts said this right here. You see this? This is what the prediction was. Okay, this is what their low prediction was. We're supposed to be in a solar cycle minimum. But if you look here, you can see the real numbers in black. Okay? So, and our numbers are already way up here. And we're not even at the center of this yet. Now that we've actually been into this a couple of years here, okay, here we are at 2022, since we've already been in here. Now they've had to readjust their model, and now look at what they're saying. 246 sunspot number groups. Well, just a second here. This is the top of the hump for the solar cycle, okay, which is an 11-year cycle. If you follow this baby straight up, and you follow the curve of this, we're gonna be way up here. You know, 400 or 500. I mean, it goes way up here. So we're gonna more sunspot numbers means more flares, more coronal mass ejections. I mean, here we'll come down here, and this is our radio flux. As you can see, just in X-ray, which is our X-ray flux. X-ray flux, we've already peaked at 133.98. Now, it does go up and down. It doesn't just go straight up. It kind of goes up and down as it's going through its cycle. So we did have 133.98. Well, the total that we were only supposed to have was 135. And we still got to go way up here? Yeah. Now, what happens is when the sun gets off a coronal mass ejection, this is LASCO C2, we can see all the charged particles going off in the air. Now, this one happens to be going away from the Earth. But what happens is that sometimes we get a little glancing blow like this, where we have one come off here and we just get a little zip, a little glancing blow. At other times, we take it right square on the chin. And that's when things get a little excitable. Okay? Now, the thing you have to understand is when the sun gives off this coronal mass ejection, boosh, it's like a punch. It's literally like a punch to the earth. Okay? And if you want to use Mike Tyson in his prime, and that's the best example I can use, that's pretty much that punch coming towards the earth. Now, even though this is quite funny, his face is quite funny, let's divert from that for a moment and just consider this being the earth. Do you see how it bounces and reverberates back? That's exactly what happens when we get a coronal mass ejection, that impacts. Now, it's not just the impact that causes some earthquakes and some tectonic plate movement, it's the bounce back, the reverberation, the woo 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 woo. That's when things really start getting moving. Okay? Now, when that happens, we typically, this right here, this is a prime example, you can see all the magnetic fields of the earth. You can see all the connection lines. Okay, that keeps us from really being torn apart. Okay, because we have the magma inside our iron core that rotates around, which actually creates our magnetic field. I mean, if you look at a magnet, it's got a north and south polarity. We have a north and south pole, and as it spins around, it creates a magnetic field, like a generator, like a magnetic generator. Okay, and this is what happens. Well, when we get that impact, whoosh, we can see that it comes back. Well, what also happens is it also snaps some of these lines because the impact is so strong. You got to remember, it's positively charged, so some of these lines will actually break, and they'll come back around here and they'll reconnect. Now, if the flare or coronal mass ejection is strong enough, it can go through multiples. Okay, and then what happens if we get a normal one? Well, let this one start up. It snaps and then comes back around to the back side of the Earth, creating 0-point energy. Well, if we have another one right behind it, we can actually be taken out by 4 or 5 decent C flares to M flares, impacting one after another after another. It can really take apart our magnetic field. Okay, and and they also ride down the lines right to our north and south pole, which are our weakest points, and that's what gives us aurora, and it can drive aurora all the way down to the equatorial plane if they be large enough. But some of you might be saying, well, wait a minute, we've had X flares and M flares and stuff in the past, and we've been doing just fine, so what's the big deal now? Well, slow your roll there, Pancho. Check this out. How many people know that our north and south pole are on the move? Let's take a look over here at the south pole. Our magnetic south pole. It's not even in Antarctica anymore. It's not even on a continent. It is in the ocean. And it's actually between here and here. It is on the move. Okay? Now our magnetic fields are actually weaker than what they were in the past. Look at the North Pole. North Pole is definitely taking a hiatus. We're like right here right now. And this is where it was 2 years ago. So now we're closer to here. And this is just as of recent. Okay, this has actually been like they've been showing this for probably the last year to 2 years. So this has not even been fully updated yet. Now with that being said, we're also speeding up in rotation. That makes for weaker magnetic fields. Weaker magnetic fields means lower coronal mass ejections and flares will have a stronger impact on the Earth. So if you want to know how bad we're taking energy from the sun, we can always check out our aurora. Okay, spaceweatherlive.com, come over here to auroral activity, and go right here to auroral activity, and this is where it'll bring you. Okay, you see your auroral activity. You can see what color it is, and you can see how far it is. Also let you know the KP index, okay, which is radiation, basically, solar radiation, which leads to aurora on the north and south pole. One of the other funny things that it does, and a lot of people are not very familiar with this, is you can see our hemispheric power. Okay, which calculates and tells you, there's lots of little things that you can read on here to kind of get yourself updated on what's going on. And here it tells you this is the North Pole and this is the South Pole. You got your 0 here, okay? North and South. You guys remember Back to the Future in gigawatts?
Reaction to generate the 1.21 gigawatts of electricity. What did I just say?
Classic.
This fucker's electrical. But I need a nuclear reaction to generate the 1.21 gigawatts of electricity. 1.21 gigawatts!
For those of you who are not very familiar with gigawatts and the power that means, let me show you. How many homes can 1.1 gigawatt power? The short answer, about 725,000 homes. Imagine being able to harness that. And that's from 1 gigawatt, from a bolt of lightning. Okay? Now, currently, right now, we are at 32 gigawatts. So let's take 725,000, multiply that times 32 gigawatts. That's 23,200,000 homes on the daytime side when we're taking that. Ain't that amazing? Imagine if we can learn how to harness that. Just a little food for thought. So keep your eyes open, no fear, and remember that love is the only way forward.